Alright y'all, I'm going to do a quick little walkthrough slash tutorial thing for the materials recitation number 3. So for the first question, derive the body relationship for a body-centered cubic crystal structure with the unit cell length A and atomic radius R. So for this one, we can look at this picture here. Each of these corners going from here to here, approximately we can see, that's going to be 1 radius. And then going across this entire circle, this entire atom is going to be 2 radii, because that's how radii work. And then we have 1 more there, because they're touching on this diagonal. So it's not the diagonal of a face, it's the diagonal of the full cube, kind of going like that. So to make our right triangle, to find that, we have that hypotenuse, come down this edge, and we go across the face at the bottom of the cube. So that's our triangle. So we have A here, and then since this is going to be A, and then going towards the back, that's going to be A, and this is the hypotenuse of that triangle. This thing at the bottom is going to be A squared plus A squared square root. So that's our bottom hypotenuse. Then we have this side length, and that's just A. So that's what we get. And this is A squared plus A squared square root squared plus A squared equals 1, 2, 3, 4R also squared. So that's that relationship just with the Pythagorean theorem. That's because then it foils out and it's fine. And the second one, for the face-centered cubic, this one you want to look at the diagonal of the face instead of the diagonal of the entire cube. So this one has 1, 2, 3, 4 radii again, but this one's just going to be A squared and A squared. It's going to give us the diagonal of the face. So A squared plus A squared equals 4R squared. Simplify, and we get this relationship. Then for part 2, when we're looking for the APF, for the body-centered cubic, the volume of atoms in the cell. So the volume of one atom is going to be the 4/3 pi r cubed, because that's the volume of a sphere. And for a body-centered cubic, that was this one. So we have our 4 corners, and then, 8 corners and 1 in the center. So for 8 corners, each one is an 1/8. So we got 4 corners divided by 8 plus 1 in the middle. That's going to give us 2 atoms in total in the unit cell. So it's 2 times that 4/3 pi r cubed, and that's going to give 8 pi r cubed all over 3. Then the total volume of the unit cell with A. So the volume of a cube is just going to be A cubed. The volume of a cube is A cubed for reasons. And then from before, I have the body-centered cubic one up here. If we solve this for A squared, then we have this, and then square root it, obviously, to get actual A. So that's square root of that, that's 4 square root 16. R square root R squared, root 3, obviously. So we have A squared times A gives us A cubed. You multiply through all the way across, and that gives us that. And this is just to the 3 halves, because I was too lazy to write square root of 3 times 3. I just smushed it all together. And then this one, calculate the APF. That's just volume of atoms divided by the total volume. So that's atoms, total volume. I put them over, and I simplified and crisscrossed everything and but I ended up with root 3 pi over 8. Now doing the same thing for face-centered cubic, it's again the volume of atoms is going to be 4/3 pi r cubed, and since for face-centered cubic, find this diagram over here, we have our 8 corners at 1/8 each, which gives us our 1, and then we have 6 faces, that's each 1/2, so that's our 1 from the corners plus the 3, because that's 6 divided by 2, and that's going to give us our 4. So that's what we're doing here. It's 4 times 4/3 pi r cubed. That's the volume of the atoms. Then from before, we calculated that A here is going to be square root 8r squared, or just root 8r, or 2 root 2, whole deal. And that's going to be our area up here. Square root of A equals that. Then we cube it. Again, it's the same thing. Then that's going to give us our total volume. Then we do volume of the atoms divided by the total volume. Again, it's just crisscrossing with the coefficients and canceling and all that. And I got root 2 pi over 6, which there is a decimal equivalent to that I don't feel like figuring out. So that's fine. And this last one with the density of iron was a little bit more tricky. So in the table, it's given that it's a body-centered cubic. So that means per unit cell, that's our 2 atoms per unit cell again. Because remember, we have our 4 corners plus 1 in the middle. Our 4 corners, 8 corners divided by 4. What? 8 corners divided by 8. And then, yeah, so then it's also given the radius is 0.126 nanometers, which is 1.26 times 10 to the negative 8 centimeters, because math. Then I looked up the molar mass, 55.845 grams per mole, and then you divide, so that's in grams per mole, so if you do have grams per mole, and you divide by Avogadro's number, which is atoms per mole. Moles cancel, you get grams per atom. So when I did that, I got 9.215 times 10 to the negative 23 grams per atom. And then I multiplied the grams per atom times our 2 atoms per unit cell to get 1.843 times 10 to the negative 22 grams per unit cell. Then, since it was the body-centered cubic, we found before, nope, not on the side, sorry. We found before for the body-centered cubic that our total volume of the unit cell is 64r cubed over 3 to the 3 halves. So that's this, 64, this is our radius from before, cubed all over 3 to the 3 halves. And that, for the volume, I got 2.46 times 10 to the negative 23rd cubic centimeters. And then density is grams per unit volume. So that's, again, our mass divided by our volume. I got 7.48 grams per centimeters cubed. The real one is 7.87, so we're pretty close, kind of like rounding, or the fact that it's not going to be perfect. Either way, but yeah. And then since they're like pretty close, that's fine. Anyways, yeah, this is my quick little walkthrough for the materials recitation. If you still have any questions, let me know. And let me know if there's any other problems or classes that you want me to explain things for. All right, bye-bye.